Hello guys, this is a presentation about managing quality and statistical process control from our group, that's group 3. The first will be explained by Reno.
What is managing quality? Quality management is the act of overseeing all activities and tasks that must be accomplished to maintain a desired level of excellence. This includes the determination of quality policy, creating and implementing quality planning and assurance, and quality control and quality improvement. Quality and strategy. Quality is a wonderful tonic for improving operations. Managing quality helps build successful strategies of differentiation, low cost, and response. Many companies have proved this statement to be true, where they have used quality as their main focus, either for the production or for the product itself. Quality affects the entire organization, from supplier to customers, and from product design to maintenance. Perhaps more important, building an organization that can achieve quality is a demanding task. A successful quality strategy begins with an organizational culture that fosters quality, followed by an understanding of the principle of quality, and then engaging employees in the necessary activities to implement the quality. When these things are done well, the organization typically satisfies its customer and obtains a competitive advantage. The ultimate goal is to win customers. Because quality causes so many other good things to happen, it is a great place to start. As you can see from the figures, it shows that improvement in quality helps firms increase sales and reduce costs, both of which can increase profitability. Increases in sales often occurs as firms speed response, increase or lower selling prices, and improve their reputation for quality products. Similarly, improved quality allows costs to drop as firm increases productivity and lower rework, scrap, and warranty costs. Implication of quality. In addition to being a critical element in operations, quality has other implications. Here are the 3 other reasons why quality is important. The first one is company reputations. An organization can expect its reputation for quality, being it good or bad, to follow it. The second one is product liability. The courts increasingly hold organizations that design, produce, or distribute faulty products or services liable for damages or injuries resulting from their use. Legislation such as Consumer Product Safety Act sets and enforces product standards by banning products that do not research those standards. The third one is global implications. In this technological age, quality is an international as well as OM concern. For both a company and country to compete effectively in a global economy, product must meet global quality, design, and price expectation. Cost of quality, or COQ. 4 major categories of costs are associated with quality, called the cost of quality. There are prevention costs, costs associated with reducing the potential for defective parts or services. The second one is appraisal cost, costs related to evaluating products, processes, parts, and services. The third one is internal failure costs that result from the production or defective part or services before delivery to customers. The fourth one is external failure costs that occur after delivering of defective part or services. Total quality management. Total quality management, or TQM, refers to a quality emphasis that encompasses the entire organization from supplier to customer. TQM stresses a commitment by management to have a continuing company-wide drive towards excellence in all aspects of product and services that are important to the customer. Each of the 10 decisions made by operation manager deals with some aspect of identifying and meeting customer expectation. Meeting those expectations require an emphasis on TQM if a firm is to compete as a leader in world markets.
I will explain with total quality management. Total quality management refers to a quality process that includes the entire organization from suppliers to customers. TQM features are a commitment by management to have a continuous company-wide drive towards excellence in all aspects of products and services that are important to the customers. Each of the 10 decisions made by operations, manager deals with some aspect of identifying and meeting customer expectations. Meeting those expectations equals an emphasis on TQM if a firm is to compete as a leader in world markets. I will explain first about the continuous improvement. Requires a never-ending process of continuous improvement that covers people, equipment, suppliers, material, and procedures. The end goal is perfection, which is never achieved but always sought. Plan, do, check, act. Walter Sheward, another pioneer in quality management, developed a circular model known as PDCA, plan, do, check, and act, as the definition of continuous improvement. The Japanese use the word kaizen to describe this ongoing process of unending improvement, the setting and achieving of ever higher goals. After that, I will explain about the Six Sigma. The term Six Sigma popularized by Motorola, Honeywell, and General Electric has two meanings in TQM. The first is statistical sense. It describes a process, product, or service with an extremely high acceptability, 99% accuracy. The second one is Sigma is a program designed to reduce defects to help lower costs and time and improve customer satisfaction. Implementing Six Sigma is a big commitment in the successful Six Sigma programs in every firm, from GE to Motorola to DuPont to Texas Instruments, require a major time commitment, especially from top management. The leaders have to formulate the plan, communicate their buy in the firm's objective, and take a visible role in setting the plans for others. Successful Six Sigma projects are clearly related to the strategic of a company. Next, employee empowerment. Employee empowerment means involving employees in every step of the production process. The task is to design equipment and process that produce the desired quality. This is the best done with a high degree of empowerment by those who understand the shortcomings of the system. Techniques for building empowerment include: first, building communication networks that include employees; second, developing open supporting supervisors; third, moving responsibility from both manager and staff to production employees; and the last, building high moral organization and using such formal organization structure as team and quality circle. After that, benchmarking. Benchmarking includes selecting a demonstrated standard of product, service, cost, or practice that represent the very best performance or process or activity very similar to your own. The steps developing this one are: first, determine what to benchmark; second, from a benchmark team; third, identify benchmark partners; fourth, collect and analyze benchmark information; and last, take action to match or exceed the benchmark. And after that, I will explain about the IT. The IT is one of the continuous improvement and import problem solving. The IT systems are designed to produce or deliver goods as they are need. The IT cuts the cost of the quality. The IT improves quality. Better quality means less inventory and a better, easier to employ the IT system. And after that, I will explain about role of inspection. Now, I will explain about tools of TQM. First, Excel form that is designed for recording data. Second, scatter diagrams, relation between two measurements. After that, histograms, value of a measurement and the frequency with which each value occurs. And after that, cause and effect diagrams, identifying the quality issues and inspection points. And particle charts, method of organizing errors, problems, or defects to help solve reports. Flow charts, process or system using annotate, box, and interconnect lines. The last, statistical process control. Monitor standard measurements and takes corrective action as the product is being produced. Role of inspection. Inspection must often be performed to ensure that process are performing to standard. This inspection can involve measurement, testing, patching, weighing, or testing of the product. sometimes even measuring it when it's doing so. A means of measuring that an operation is producing at the quality level spec. Moreover, inspections are expensive and do not add value to the product. When and where to inspect? First, at your supplier's plant while the supplier is producing. Second, at your facility with ownership of goods from your supplier. Third, before costly or irreversible process. Fourth, during the step-by-step production process. Five, when production or service is complete. Six, before delivery to your customers. And seven, at the point of customer contact. Source inspection. Controlling or monitoring in the point of production or purchase at the source. The best inspection can be taught as no inspection at all. Inspection is always done at the source. It is doing the job properly with the operator ensuring that the result and idea is at each supplier. Process and include reach the next step and process with the customer. Ensuring proper product to next customer. This inspection may be assisted by the use of checklists and controls such a file device called the Pokayoke, numbered from the Japanese. Pokayoke literally translates to mistake proofing. It has to come to mean the device or technique that ensures the protection. After that, there is a checklist. Our type of Pokayoke to help ensure consistency and completeness in carrying out of the plan. A basic checklist to do a list. This tool may take the form of a perfect line checklist, used by airplane pilots, vehicle safety checklist, used by doctors, or software quality assurance list used by programmers. Service industry inspection. In service-oriented organizations, inspection points can be assigned at a wide range of locations. The operation manager must decide where inspections are justified and may find the 7 tools of TCM useful when making this job. Inspection of attribute versus variable. It's attribute inspection. It's inspection that classifies items as being either good or defective. The variable inspection. Classification of inspect items is rolling on continuous scale, such as dimension or
TQM in services. The personal component of services is more difficult to measure than the quality of the tangible component. Generally, the user of service, like the user of goods, have features in mind that form a basis for comparison among alternatives. Lack of any one feature may eliminate the service from further considerations. Quality also may be perceived as a bundle of attributes in many lesser characteristics are superior to those of competitors. This approach to product comparison differs little between goods and services. However, what is very different about the selections of services in the poor definitions of the number 1, intangible differences between products, and number 2, the intangible expectation customers have of those products. Marketing issues such as advertising, image, and promotion can make a difference. The operation manager plays a significant role in addressing several major aspects of service quality. First, the tangible component of many services is important. How well the service is designed and produced does make a difference. This might be how accurate, clear, and complete your checkout bill at the hotel is, how warm the food is at the Taco Bell, or how well you can run after you pick it up and repair shop. Second, another aspect of service and service quality in the process. An operation manager can design processes that have this attribute and can ensure their quality through the TQM techniques discussed in this chapter. Third, the operation manager should realize that the customer's expectations are the standards against which the service is judged. Customers' perception of service quality result from a comparison of their before service expectation with their actual service expectation. In other words, service quality is judged on the basis of whether it meets the expectation or not. The manager may be able to influence both of the quality of the service and the expectation.
Statistical process control is application of statistical technique to ensure that process meets standards. All processes are subject to certain degree and variability. Control charts. The process of building control charts is based on the concept presented in photo 1. This photo shows three distributions that are the result of outputs from three types of process.
The central limit theorem. The theoretical foundation for X-charts is the central limit theorem. This theorem states that regardless of the distribution of the population, the distribution of Xs, each of which is a mean of a sample drawn from the population, will tend to follow a normal curve as the number of samples increases. Setting mean chart limits. X-charts. If we know through past data the standard deviation of the population or process is, we can set upper and lower control limits cubed by using these formulas. Setting range chart limits or R-chart. The theory behind the control charts for ranges is the same as that for process average control charts. Limits are established that contain plus or minus 3 standard deviations of the distribution for the average range R. We can use the following equations to set the upper and lower control limits for ranges. Control charts for attributes. There are two kinds of attribute control charts. First, those that measure the percent defective in a sample, called P-charts. And second, those that count the number of defects, called C-charts. P-charts. Using P-charts is the safe way to control attributes. The procedure resembles the X-chart approach, which is also based on the central limit theorem. For P-chart upper and lower control limits, we can use the formulas below. C-chart. We use C-charts to control the number of defects per unit of output or per insurance record in the preceding case. The Poisson probability distribution 5, which has a variance equal to its mean, is the basis for C-charts. Because C is the mean number of defects per unit, the standard deviation is equal to 2C. To compute 99.73% control limits for C, we use this formula.
Process capability. Statistical process control, meaning keeping a process in control. This means that the natural variations of the process must be stable. However, a process that is statistical control may not yield goods or service that meet their design specification or tolerance. In other words, the variation should be small enough to produce consistent output within specifications. The ability of a process to meet design specifications, which are set by engineering, design, or customer requirement, is called process capability. Even though the process may be statistically in control or stable, the output of that process may not conform to specifications. Process capability ratio, or CP. For a process to be capable, its value must fall within upper and lower specification. This typically means that process capability is within around 3 standard deviations from the process mean. Because this range is 6 standard deviations, a capable process tolerance, which is the difference between the upper and lower specifications, must be greater than or equal to 6. The process capability ratio, or CP, is computed as below. Next, the Process Capability Index, or CPX. The Process Capability Index, or CPX, measures the difference between the desired and actual dimensions of goods or services produced. The formula for it is acceptance sampling. Acceptance sampling is a form of testing that involves taking random samples of lots or batches of finished products and measuring them against predetermined standards. Sampling is more economical than 100% inspections. The quality of the samples is used to judge the quality of all items in the lots or batches. Operating Characteristic Curve. The operating characteristic, or OC, curve describes how well an acceptance plan discriminates between good and bad lots. A curve pertains to a specific plan, that is, to combination of N, which is the sample size, and C, acceptance level. It is intended to show the probability that the plan will accept lots of various quality levels. The acceptable quality level, or AQL, is the poorest level of quality that we are willing to accept. In other words, we wish to accept lots that have this or better level of quality, but no worse. If an acceptance quality level is 20 defects in a lot of 1,000 items or part, then the AQL is 20 greater than 1,000 equals 2 defectives. The lot tolerance percentage defective, or LTPD, is the quality level of a lot that we consider bad. We wish to reject lots that have this or a poorer level of quality. If it is agreed that the unacceptable quality level is 70 defects in a lot of 1,000, then the LTPD is 70 greater than 1,000 equals 7 defective. Average outgoing quality. In most sampling plans, when a lot is rejected, the entire lot is inspected and all defective items replaced. Use of this replacement technique improves the average outgoing quality in terms of percentage defective. In fact, given any sampling plan that replaces all defective items encountered and the true incoming percent defective for the lot, it is possible to determine the average outgoing quality, or AOQ, in percentage defective. The equation for AOQ is stated like this. That's all, and thank you for your attention.